Okay, good morning. My name is Meng. So my name is Meng Lu. I'm from Utrecht University in the Netherlands, and now I'm working a project called Global and GeoHealth Data Center. I was a PhD student in Etzer's group a few years ago, and since it feels like coming back home. And I was also a participant of the GeoStart summer school in 2014. So I am enjoying as much as 5 years ago. So now I'm trying to develop myself in health geography, but I'm still very much interested in spatial-temporal data analysis and geocomputation. So you just look at the local scale studies, and now we look at the global scale study in air pollution. So before we look at the global air pollution modeling, I want to give a brief background about the spatial-temporal epidemiology and the challenge of global air pollution mapping. So spatial-temporal epidemiology is the description and analysis of geographical data, specifically health outcomes, and the factors that may explain the variations in those health outcomes over space. And the environmental epidemiology has a focus on the exposure, on the environmental exposure on human health. That's also where I'm trying to develop myself in. Spatial-temporal epidemiology has a long history, origins to the mid-80s, when John Snow, who's acknowledged as the founder of the epidemiology, tries to identify the causes of the outbreak of cholera. So at that time, people still believe that the cholera is transmitted through a noxiously bad form of air, and there's no germ theory. So he studied the spatial patterns of those incidences, and then he found that most of those cholera cases occurred within the distance of a water pump. So he identified that's a contamination source and disabled the water pump, and the cholera cases went down. So that's a very historical and legendary study. And nowadays, the environmental epidemiology is vigorously growing. So it's very interdisciplinary, so it's the change with advancement in environmental science, data analysis, sensors, techniques, and epidemiology. This field is really evolving, and many of the concepts and perspectives also change. So in 2005, there's a concept called exposome that raised lots of attention, and it's very important because it stresses the exposure at personal level. So what you eat and drink, where you live and work, and how much exercise you do, they contribute largely to whether you're going to develop a disease or not. So that's also a big motivation that we need to model the spatial-temporal variations of the environment and then have them mapped in details, because then by looking at the spatial-temporal tracks, we can assess the personal exposure. So in our case, we look at the nitrogen dioxide. It is highly traffic-related and very localized, so it makes great sense to have very high-resolution maps. Global air pollution mapping is a very intriguing topic and very important for global health studies, because if you have one global model, so one map, then those health studies that are carried out in different areas of the globe, they are comparable, and that's very important for the global health studies. And also on the mapping side, the ground monitors, they are unequally distributed. So you see they are very sparsely distributed in Russia and Africa, South Africa, and Africa and South America. And also from the right figure, it's a study that is carried out using remote sensing data to predict air pollution. And the deeper the color, you see the prediction is more reliable. it's more depending on the satellite measurements because there's very ground sensors there. And it's a very big challenge. So from where you can gather the data, and also at the global scale, the data, everything becomes very heterogeneous. And I completely agree that at the regional level, it's already difficult enough to do the mapping. But there's a study of Larkin published in 2017. So it's the first global nitrogen dioxide mapping at 100-meter resolution, and it's still the only model that is available. So that one, it only uses a simple linear regression model, but the sensitivity analysis I found is very inspiring. So it inspired me to explore the global mapping and to see, so with all the data we get and the methods that we think would be useful, how far away are we still from global mapping? So I carried out the study to further improvement, not just in terms of the prediction accuracy, but also in understanding more about the process, so where are the limitations. So I also used different statistical learning methods to also look at what the model could tell me, and if they could flexibly reflect those relationships between predictors and air pollutant global-wise. And then I compared between different national models to see how those relationships vary within countries, and then compared with the global model to see what information is gained or lost if I use the global model. And the study is also very much motivated by the availability, so the launching of the Sentinel-5 precursor satellite in 2017. So the Sentinel-5 precursor satellite carries the Topomi instrument that measures gaseous air pollutant at 7 by 7 kilometer resolution, which is unprecedentedly high. And you can see it compared to the present satellite OMI. You can see how much detail it could measure. So you can see how coarse the OMI cells is compared to the Topomi. So more specifically, I compared different statistical learning methods. I used 3 tree-based methods, so random forest, stochastic, gradient boosting, and extreme gradient boosting, which is called XGBoost. So you are probably more familiar with the first two, and the XGBoost is a bit new. It's won the Kaggle machine learning prediction competition, and so it becomes quite popular. So that one, basically, it has a regularization term to prevent model fitting. And I used the regularized regression methods, so the ridge lasso, which many people also call it lasso, and elastic net, that they use different kind of penalties also to prevent model overfitting, and also compared it with just a basic linear regression. And I divided 4 national models. In the parentheses, you see the number of ground station measurements available in those countries, and then do the comparison and also compare it with the global model. And then we involved 3 remote sensing satellites, remote sensing products, and then also studied the sensitivity analysis, studied the contribution of the Topomi, how could it contribute to the global mapping. And we also additionally separated between day and night, because at daytime, the traffic, the influence is probably bigger to the air pollutant compared to the nighttime. And this is also important for the next step of the exposure assessment, because human activity is also very different between day and night. This is the global model prediction accuracy. So different color bars shows different error indicators. So the lower, the better. And from left to right, you see different methods. The first is the linear regression, and the three next to it are the regularized linear regression, and the last three are the regression tree-based method. So you actually see that the accuracy between the three regression tree-based methods are very similar to each other, and they perform better than other methods. And then we also compare between national and global models. So I'm showing here the left figure is for the random forest prediction, and the right for the lasso prediction. And the orange bars, the using global model, and the green bar using local model. So we can actually conclude it here that with the random forest, the difference between global and local models are smaller than using lasso. So it means for global mapping, the random forest might be more useful. No, that's not the end of the story. So then I look at the spatial predictions. So at the upper plot shows, so those are the examples of a city in Germany, and the upper plot shows the national model predictions, and the bottom plot shows the global model prediction. And from left to right, the lasso, using lasso, random forest, and the XGBoost. So you can actually see, and I was also quite surprised how different they are. So even though, especially between these two regression tree-based learning methods, they achieved very similar accuracy, but their spatial patterns are so different. So you see, for example, the national model of the random forest, it didn't pick up the highway, and the XGBoost, the national models, it pick up the highway, and it fits lots of details in there. And also, even though the global and national models of random forest in terms of accuracy are quite different. You can also see how are quite similar, so you can also see how different they are. So the national model is stressed a lot on the local roads, but the global model not so much. So I would also like to hear your opinions about these models. So if you choose one of them for the nitrogen dioxide mapping in Germany, so which one would you recommend? Just based on these spatial patterns, if there's no additional information that is available. So anyone would pick the lasso national model, or the random national model, or the SG national model, or the global lasso model, global random forest, XGBoost, global. Okay, yes, thank you. So we will discuss more about this later in the afternoon. And in the afternoon, I will also introduce more about the air pollution modeling and the statistical methods, statistical learning methods, but I will make it complementary to what you have learned in your machine learning courses. And then we will go in depth into the modeling process to really look at the data. So from the data visualization to preliminary examination, and then to the modeling, and then the spatial prediction, looking at the results. Yeah, thank you. Oops.
If not, you can keep them to the afternoon. Okay, then